Welcome back. Last time we replaced curves with their tangent lines and turned linear approximation into a computational sledgehammer. Square roots by hand, error propagation by differential, the whole engineering linearization trick. Today we take the derivative seriously as a diagnostic tool. We ask what the derivative tells us about the shape of a curve, specifically where it peaks and where it bottoms out. The answer is one of the oldest observations in calculus. Due to Fermat in 1638, at a peak or valley, the tangent line is flat. We'll make that precise, define critical points, classify them with the first derivative test, and then earn the theorem that quietly powers half of single-variable calculus, the mean value theorem. It says the average slope on an interval is hit exactly by the instantaneous slope somewhere inside. Sounds innocent, has enormous consequences. We'll prove it from Rolle's theorem, walk through two concrete examples, and trace the historical arc from Fermat to Rolle to Lagrange to Cauchy. Let's go. Definitions first. A local maximum of f at the point C is a place where f of c is greater than or equal to f of x for every x in some open interval around C. In words, C beats its neighbors. Not the whole world, just the immediate neighborhood. Local minimum is the mirror image, f of c is less than or equal to f of x nearby. The word local is doing work. A local maximum doesn't have to be the highest point on the whole graph, it just has to be the highest point in some neighborhood. A mountain trail can have many local peaks and valleys without any of them being Everest or Death Valley. We use the word extremum as the umbrella term for either max or min, and the plural is extrema, both Latin. We're after a tool that finds them all. Picture. The blue curve is some smooth function f. There are two highlighted points, a local maximum at C1 and a local minimum at C2. At each of them, I've drawn the tangent line in red, and you can see by inspection that both tangent lines are horizontal. They have slope 0. This is the geometric fact we want to formalize. At a peak, the curve has just finished going up and is about to start going down, so the instantaneous slope at the peak itself must be 0. Anything else would mean the curve is still moving vertically through the peak, contradicting that it's a peak. Same logic at the valley, with the signs flipped. The horizontal tangent is the signature of an extremum. Now the central definition. A critical point of f is an input C where either f prime of c equals 0, flat tangent, or where f prime of c doesn't exist at all. Two ways the tangent can fail to be a slanted line. First, it can be horizontal, slope 0. Second, there can be no tangent line in the ordinary sense, a corner like absolute value at the origin, a cusp like x to the 2/3 at the origin, a vertical tangent like cube root of x at the origin. At all of those, f prime fails to exist as a finite number. Both kinds of critical points are candidates for local extrema. You have to check both. Most calculus problems lean on the smooth case, f prime equals 0, because the function is differentiable everywhere. But don't forget the second case exists, especially in problems involving absolute values or piecewise functions. Fermat's theorem. If f has a local extremum at the point C and the derivative f prime of c exists, then f prime of c must equal 0. Pierre de Fermat noticed this in 1638, decades before calculus had its modern form, and he used it to find maxima and minima of polynomials by setting derivatives, though he didn't call them derivatives, to 0. The proof is short and worth seeing. Suppose c is a local max. Then f of c is greater than or equal to f of c plus h for all sufficiently small h, positive or negative. Form the difference quotient. F of c plus h minus f of c divided by h. The numerator is non-positive. If h is positive, the quotient is non-positive. If h is negative, the quotient is non-negative. Now take the limit as h goes to 0. From the right, the limit is less than or equal to 0. From the left, the limit is greater than or equal to 0. Both one-sided limits equal f prime of c because the derivative exists. So f prime of c is both at most 0 and at least 0. It's 0. Local minima work the same way with signs flipped. The whole proof is two inequalities and a sandwich. Beautiful. A crucial subtlety. Fermat's theorem runs one way. If you have a local extremum with the derivative defined, then the derivative is 0. So every smooth extremum is a critical point. The converse does not hold. Not every critical point is an extremum. The standard counterexample, f of x equals x cubed at x equals 0. The derivative is 3x squared, which equals 0 at 0. So 0 is a critical point. But the function is strictly increasing everywhere. To the left of 0x cubed is negative, to the right it's positive, and at 0 it just has a flat spot in the middle of an otherwise relentless climb. No max, no min. So critical points are a necessary condition for local extrema, but not sufficient. The practical strategy, find all critical points, which gives you a finite list of candidates. Then classify each candidate as max, min, or neither, using a separate test. That test is what comes next. The first derivative test. At a critical point C, look at the sign of f prime just to the left and just to the right. 4 cases. Plus on the left, minus on the right, the function was increasing, then started decreasing. That's a local maximum, the classic peak shape. Minus on the left, plus on the right, the function was decreasing, then started increasing. That's a local minimum, the valley. Plus on both sides, increasing the whole way, with a flat tangent at c but no change in direction. Not an extremum, just a flat spot mid-climb, like x cubed at 0. Minus on both sides the mirror image, also not an extremum. The rule of thumb, a sign change in f prime classifies the extremum. No sign change means no extremum. To use the test, find f prime. Find the critical points where it's 0 or undefined, then check the sign of f prime in each interval between consecutive critical points. This is the sign chart you've seen in every calculus class. First worked example. Take f of x equals x cubed minus 3x. Find and classify all the critical points. Compute the derivative. F prime of x equals 3x squared minus 3, which factors as 3 times the quantity x minus 1 times x plus 1. Set equal to 0, x equals plus or minus 1. 2 critical points. No places where the derivative fails to exist. This is a polynomial. Now the sign chart. Pick a test point in each of the 3 intervals. Far left, x equals minus 2, f prime is 12 minus 3 equals 9 positive. In the middle, x equals 0, f prime is 0 minus 3 equals minus 3 negative. Far right, x equals 2, f prime is 12 minus 3 equals 9, positive again. So the pattern is plus, then minus, then plus. At x equals minus 1, f prime goes from plus to minus, local maximum. At x equals 1, f prime goes from minus to plus, local minimum. To get the actual values, plug in. F of minus 1 is minus 1 plus 3 equals 2. F of 1 is 1 minus 3 equals minus 2. Done. The function rises, peaks at minus 1, 2, falls to a valley at 1, minus 2, then rises again. Classic cubic with a wiggle shape. Rolle's theorem. Michel Rolle published this in 1691. Statement: if f is continuous on the closed interval from a to b, differentiable on the open interval from a to b, and the function takes the same value at both endpoints, f of a equals f of b, then there exists at least one point c strictly between a and b where f prime of c is 0. Geometrically, if a smooth curve starts and ends at the same height, somewhere in between the tangent line must be horizontal. It has to come back down, or come back up, or both. Either way, there's a turnaround, and at the turnaround, the slope is 0. The proof relies on the extreme value theorem from continuity. A continuous function on a closed bounded interval must attain its absolute maximum and minimum. Apply that to f. If the maximum or minimum is attained in the interior of the interval, that point is a local extremum, and Fermat's theorem tells us the derivative is 0 there. If both the max and the min are attained at the endpoints, and since f of a equals f of b, that means the max and the min are equal, then f is constant on the whole interval, and the derivative is 0 everywhere. Either way, c exists. Clean argument, 2 cases. Picture. The blue curve starts at the point a, f of a, ends at the point b, f of b, and those two heights are equal, shown by the dashed horizontal line connecting them. The curve in between is smooth and continuous. Visually, the curve has to peak somewhere between a and b, and at the peak. Point c, the tangent line in red, is horizontal. That's Rolle's conclusion. The picture might also have a valley, or several peaks and valleys depending on what the function does. Rolle guarantees at least one place where the tangent is flat, not necessarily exactly one. The simplest case is what we drew. One bump, one flat tangent at the top. Now the main theorem. The mean value theorem, often abbreviated MVT. Suppose f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Then there exists a point c strictly between a and b such that f prime of c equals the difference quotient f of b minus f of a, all over b minus a. In words, the instantaneous slope at some interior point equals the average slope over the whole interval. Geometrically, the tangent line at c is parallel to the secant line connecting the two endpoints of the curve. The secant is the average slope, the tangent is the instantaneous slope. The theorem says they coincide somewhere. Notice that Rolle's theorem is the special case where f of a equals f of b, so the average slope is 0, and the MVT degenerates to there exists c with f prime of c equals 0. So Rolle is a baby version of the MVT, and we'll prove the MVT by reducing it to Rolle, which is the easier theorem. Picture. The blue curve goes from the point to f of a up to the point b, f of b. Draw the secant line, the dashed red line connecting the two endpoints of the curve. Its slope is the average rate of change, f of b minus f of a, all over b minus a. The MVT says, somewhere between a and b, there's a point c, where the tangent line to the curve, the solid red line, has the same slope as the secant. The two red lines are parallel. The tangent touches the curve at the single point c, f of c. The secant cuts the curve at both endpoints. Their slopes are equal at exactly that interior point. Visually, this is just saying if you're driving from A to B and your average speed is 60 miles per hour, then at some instant during the trip your speedometer read exactly 60. Has to. Here's the proof of the MVT from Rolle's theorem. It's one of the cleanest tricks in calculus and worth seeing once. The idea Rolle requires equal endpoints. Our function f doesn't have equal endpoints, so we subtract off the secant line, which tilts the picture so that the tilted version does have equal endpoints, and then we apply Rolle to that tilted version. Let capital S of x be the secant line, f of a, plus the average slope times the quantity x minus a. By construction, capital S of a equals f of a and capital S of b equals f of b. Now to find g of x equals f of x minus capital S of x. This g is the difference between the curve and the secant. Check the conditions. G of a equals f of a minus capital S of a equals 0. G of b equals f of b minus capital S of b equals 0. So g has equal endpoint values, both 0. G is continuous and differentiable wherever f is, since capital S is a polynomial. So g satisfies the hypotheses of Rolle's theorem. Apply Rolle, there exists c in the open interval with g prime of c equals 0. But g prime of x equals f prime of x minus the constant slope of capital S, which is f of b minus f of a over b minus a. So g prime of c equals 0 means f prime of c equals that average slope. That's the MVT. Done. The whole proof is subtract the secant, get equal endpoints, apply Rolle. 3 lines. Second worked example. Apply the mean value theorem to f of x equals x squared on the interval from 0 to 2. Compute the average slope. F of 2 is 4, f of 0 is 0, the interval has length 2, so the average slope is 4 divided by 2 equals 2. Now we want c such that f prime of c equals 2. The derivative is f prime of x equals 2x. Set 2c equals 2, get c equals 1. Sanity check c equals 1 is strictly between 0 and 2. Good. The MVT predicts exactly that point. The geometry, the secant from the origin to the point 2, 4 has slope 2. The tangent line at the point 1, 1, that is, at c equals 1, also has slope 2. The two lines are parallel. You can draw it, the secant slices through the parabola, the tangent kisses it at the midpoint, and they're visibly parallel. This is the simplest concrete MVT example you'll ever do, and it's instructive precisely because the answer comes out so clean. For more complicated functions, c might not be solvable in closed form, but the MVT still guarantees it exists. A historical aside. Pierre de Fermat around 1638 was the first to articulate that maxima and minima of a polynomial correspond to roots of what we now call its derivative. He didn't have the derivative as such, he had a procedure called adequality, where you set f of x approximately equal to f of x plus e simplify, divide by e, and then set e to 0. The modern derivative is hiding in plain sight. Michel Rolle published his eponymous theorem in 1691, originally as a result about polynomials with equal endpoint values. Ironically, Rolle was a critic of the new calculus and considered it a collection of ingenious fallacies, yet his theorem became central to calculus's foundations. Joseph Louis Lagrange, around 1797, stated the mean value theorem as part of his ambitious and ultimately doomed attempt to base all of calculus on Taylor's series without limits. Lagrange's proof had gaps. The first modern, rigorous proof of the MVT came from Augustin Louis Cauchy in the 1820s using the epsilon delta machinery he developed for his course analyze. Cauchy's proof is essentially the one we just gave. Define g, apply Rolle. With Cauchy, calculus stops being a powerful but shaky bag of tricks and starts being a rigorous mathematical theory. The MVT sits right at that hinge. Why does the MVT matter so much? Because it is the bridge between local information, the derivative at a point, and global behavior, the function over an entire interval. You almost never set out to apply the MVT in a practical problem, but it sits underneath an enormous number of results you do use. Let me list some. First, if f prime is identically 0 on an interval, then f is constant on that interval. The proof, take any 2 points, apply MVT, the slope between them is 0, so they have the same value, constant. Second, if f prime is positive on an interval, f is strictly increasing on that interval, same argument. Third, L'Hopital's rule for indeterminate forms is proved using a generalized MVT. Fourth, antiderivatives are unique up to a constant, because if two functions have the same derivative, their difference has derivative 0, hence is constant. Fifth, Taylor's theorem and its error term. The remainder formula uses the MVT. Sixth, in differential equations, the existence and uniqueness theorem due to Picard and Lindelöf uses the MVT to bound the difference between successive iterates. The MVT is the workhorse. It's the bridge from instantaneous to global. Almost every other theorem in single variable calculus stands on top of it. Where we landed. A local maximum is a point that beats its neighbors, a local minimum is one that undercuts them, an extremum is either kind. A critical point is where the derivative is 0 or fails to exist. Both are candidates for extrema. Fermat's theorem says every smooth extremum is a critical point, necessary but not sufficient, since x cubed at 0 is a critical point with no extremum there. The first derivative test classifies critical points by the sign change of f prime. Plus to minus is a max, minus to plus is a min. No sign change is neither. We classified x cubed minus 3x, local max at -1, local min at 1. Rolle's theorem says a smooth curve with equal endpoint values has a horizontal tangent somewhere in between. The mean value theorem says, more generally, that on any smooth interval, the tangent slope equals the secant slope somewhere. Average rate equals instantaneous rate. We proved it by subtracting off the secant and applying Rolle. We worked x squared on 0 to 2 and found the witness c equals 1. Historically, Fermat 1638, Rolle 1691, Lagrange around 1797, Cauchy's rigorous proof in the 1820s, and we noted that the MVT is the bridge from instantaneous to global, the workhorse underneath the rest of single-variable calculus. Next time, episode 12, the second derivative, concavity and inflection points. We use f double prime to classify the shape of a curve and the type of a critical point, faster than the first derivative test in many cases. See you in episode 12. The mean value theorem is calculus, pointing out that you cannot travel from A to B on a smooth path without, at some moment, going exactly the average speed. The channel works the same way. Average growth is just the sum of individual moments of someone clicking subscribe. One of those moments could be you. Thanks for being part of the average. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.